Welcome to Careless Coder. Today, Commodore 64 Assembly, Lesson 4. Motherfucker! So today we're going to program that infamous Commodore 64 one-line basic program that generates a maze. But we're going to generate it faster, and we're actually going to use the SID chip to generate random numbers by using the noise generator. So let's jump in. So today we're going to implement this one-liner that we have all seen in BASIC that generates this slash and backslash maze in assembly. Now this uses a random generator that is a linear shift feedback register that is not really that great. We are actually going to use the noise generator in the SID chip. Now noise is random by nature, that's why it makes that noisy sound. It's noise. It's random. However, the noise generator in the SID chip is not what they call an open bias or an open collector noise generator. It's actually digital. It's also a linear shift feedback register, but it has more positions than this one. It has about 8 million different positions before it repeats itself. So let's set up the SID. So first we set up the frequency of voice 3, because voice 3 is the only voice that has a noise generator. That's something that you need to know, or you can find in your developer's manual. And that is at memory address D40E. And I happen to know a lot of these, but you probably not, because you're new to this, so you need to Google it. So in that case you would Google for memory addresses of SID chip Commodore 64 and you get to this page. And then you see the SID has 3 voices. Voice 1, voice 2 and voice 3. Now voice 3 is the only one that has the noise generator, like I said before. But you could be misled by this document, because obviously the control register are implemented the same, but the voice 1 and voice 2 do not have this noise. So the documentation actually is faulty. It should have said noise not applicable, noise not applicable, and here noise. And I said we're going to set the high byte to FF and the low byte to FF and the high byte to FF, and that is the frequency. FF is the highest frequency that we can have, and in that case we also get the numbers the more quickly and more randomly than if we have a lower noise. I'm not going to define the high byte, I'm just doing the +1, because otherwise we get too many constants and we only use it once. So we need to set the control register. Let's control equals, and let's look that up. What is the control register for voice 3? Voice 3 control register is D412. Let's copy that. And the wave, what is the noise wave? Then we need to set 1 0 0 0 0 0 0 0 here, because we only need the noise. So that's 128. SID wave noise is 128 ATX. Noise. All right, and then we need to have a constant set up for the oscillator 3 read only. And that is this value. And what this value will hold is the actual value that is pushed to the digital to analog converter at the moment of reading. And since we are having a noise, it will be a random value. So we put that there. And let's also do a constant for the kernel character out, which is $FFD2. Use that so much that I remember that. But you just Google for kernel calls C64 and you will find that here. Character out, and it says input A, that's your accumulator, the A register, that's the byte to write. And if we have not done an open or a check out, it will print to the screen. And that's basically what we're going to do. So we set up all our hardware constants. Let's do the basic upstart 2 to main, And let's implement main. We're not going to do use a return from subroutine. We're going to actually jump to a loop. Let's create a loop here, loop. And we're first going to jump to set up the SID chip for a noise generation. Setup SID for noise. For Boise. Terrible, terrible place. Sorry if you're from Boise, but oh my god, it's horrible. I want a capital N there. Thank you. Setup SID for noise. We're going to return from this because this is actually a subroutine. And I said we're going to set the frequency in the low byte and the high byte to the highest value. So that is FF. So we load FF in A. So we can store what is in A in the SID voice low byte and in the SID voice low byte +1, the highest frequency. And then let's load in A the immediate value of the wave table, wave voice. No, it's noise. Noise. The wave table is noise. Noise. Ah, jeez. I am terrible today. Spend a long time in the car. And we store that in the SID control register. So we basically set the highest frequency in voice 3 that we have, that's the FF. Set it to 128, which is noise. And let's store in A that 128. So now we have set up the SID chip to play noise, but the volume is off. That's the default, so we don't hear it. So that is done. So now we can actually load in A that random character, the SID read from oscillator 3, the value. So now we have a random value in A. And basically what we will do is we check if it's an even value, then we print a backslash. And if it's an odd value, we print a forward slash. Easy enough. And let's call that get maze character. And after that, we will print that character because it will be in A. We will set the character that we return in A. So we can do the kernel out. And just let us implement the get maze character. We're going to return from it. Now the easiest way to compare if something is odd or even is to end it with 1. So currently we have a random value in A. We're going to end what is in A with 1. And if the lowest bit is set to 1, then it is odd. If it is set to 0, it's even. And we can quickly check whether it's odd or even. We don't need to compare with 0 because this will return 0 or 1 as we saw. Let's do that. Let's have the value 10 in A and we end it with 1. We should get the value 0, yes. If we have the value 11, then this is set and it's an odd value with 1. We should get 1. There we go. So it's really easy. Now we're going to use something that is kick assembler specific. This is a label, a very short label. And this is the amount of this label to jump. So if we have, for example, 2 of these, which we're going to have, then if we jump to plus, we jump to this one. If we jump to plus plus, we jump to this one. And even if we add another one, and plus plus plus, we would jump to this one. So this allows you to have a lot less characters. But first let me do this and let's say if and A with 1, if A and 1 equals 0, then set A, then let's do this, A is / and otherwise else A is \. So if it's equal, then the 0 bit is set, and we say if we want 0, we're going to jump to that label of exclamation mark, and we set the /. So we load A with, I believe it's 110. Let's check that again. Those I don't remember. / here, / is indeed 110. And else, this is the else, we load with 109. And of course, now we need to jump over this one to the RTS, otherwise we always will return 110. That's not what we want. So we just put that same label again, and we jump to exclamation mark ++. So we jump over this instruction to this one. So ++. So your code is a lot cleaner and smaller if you use this. And we already do the character out, so this should actually work. Last famous words. And it does. And let's compare the speed with this one. Yeah. Now, obviously, using the kernel character out is not the fastest way. We could scroll this a lot faster if we actually shift everything up. But then we need to have a 16-bit subtraction, and we have not yet taught that. So that's something that we will cover. But yeah, this is a nice, honest comparison also. So look at this. It's again about 10 times faster. So there you have it. A nice, fast scrolling maze with not too many lines. And we already learned how to use the SID, how to control those memory blocks, and we cover that more and more as we continue and get more Commodore 64 specific. So I hope you learned something, and see you in the next one.